Alright, so I know I said we were going to talk about cyclic groups next, and we generally are, but I thought I'd throw in another video on homomorphisms, simply because I tend to think that homomorphisms are the most important thing to understand completely. So with that said, let's prove a few more theorems and give a few more examples of homomorphisms. Alright, so for our first theorem, every group homomorphism phi from G to H is an epimorphism onto its image. In other words, it is a surjective homomorphism. So to see this is true, there's only really two things we need to note. One, every mapping, every function is surjective onto its image, right? So if we have a set A and a set B, and we have a function between them, we'll call it f, and by definition, a function is such that for every element in A, there exists an element in B, such that f of A equals B, right? Every input has a single output. However, we don't require that every element in the set B gets mapped to, right? There's just some subset, which we call the image of A under F, or f of A, which is the set of all outputs that actually get mapped to. But by definition then, within this image set, there exists some element in A such that f of that element is in there. Since all group homomorphisms to begin with are mappings, this must be true of them as well, that they are always surjective onto their image. So we write that phi from the group G to the image of G under the map phi is a surjective mapping, by definition. Now the second thing we want to note is that the image of a group under a group homomorphism is always a group, right? We proved this before. So that phi of G, or if you like, you could also call this the image under phi, right, is a subgroup of the group H. Thus, if we just consider the homomorphism from G to the image of G instead of G to the whole group H, because it is not necessarily onto, then this is a surjective mapping, which is also a homomorphism because the image is a group. Hence, by these two things, phi from G to the image of G is an epimorphism. Alright, so the second theorem I want to talk about is that if phi is a group homomorphism between G and H, and if G is an abelian group, right, that means the commutative property is satisfied, then the image under that map is also an abelian group. Now, let me first note what this is not saying. It's not saying that H is an abelian group. All it's saying is that H contains an abelian subgroup, the image of G under phi. It may also turn out to be true that H is an abelian group, but it's not required. So to prove this, we're going to let A and B be two arbitrary elements in the image under phi. But since it is the image set, we know there must exist elements, we'll call them capital A and capital B, in the group G, such that capital A maps under A to little a, and capital B maps under phi, to little b. So we can write the product A times B as phi of big A times phi of big B. But since phi is a group homomorphism, and we know it preserves products, this means that this is equal to phi of A times B. Now we said that G is an abelian group, so that means A times B must be equal to B times A. Now, once again, phi is a group homomorphism, preserves multiplication, so this is equal to phi of B times phi of A. But now look what we've shown, right? Phi of B is equal to B and phi of A is equal to little a. That means that because G is an abelian group, for any two elements A and B in the image of G under phi, AB is equal to BA. In other words, it is an abelian group. Alright, last time I showed you that the composition of two group homomorphisms is also a group homomorphism. In other words, if we have alpha and beta, and they're both group homomorphisms between G and H and K respectively, then we can always find a group homomorphism gamma between G and K. And this, of course, is the idea that powers the automorphism group. Not only can you compose bijections to get other bijections, but you can compose operation-preserving bijections to get another operation-preserving bijection. And this does hold more generally for homomorphisms, not necessarily only isomorphisms. Suppose now that we have a group homomorphism going from G to H and another one going from G to K. Can we prove that there exists a homomorphism going from, say, H to K? Alright, theorem. Let alpha from G to H and beta from G to K be group homomorphisms, and let alpha be surjective or onto H. Then there exists a mapping from H to K, which we'll call gamma, such that gamma is a group homomorphism of H into K. This theorem is an example of what we would call a universal mapping property, because it's going to actually hold true in more contexts than just the group homomorphism context. Later, when you study rings or other objects, there's going to be a similar theorem that holds for them. And it makes you wonder, does this hold more generally? And this is the idea behind introducing categories, which we're not going to talk about. But the whole universal mapping property is a signature thing from category theory. Look it up. Alright, first I'd like to make a little note. We assume that alpha is onto. It's not actually necessary to assume that alpha is onto because of the first theorem today, where we said that any group homomorphism is an epimorphism onto its image. So instead of considering alpha onto, we could just consider it a normal group homomorphism, and then instead imply the existence of a mapping from, say, the image under alpha to K instead of H to K. But to make it look pretty, we're going to just assume alpha is surjective and we'll have a mapping from H to K. Alright, so our strategy is going to be to first construct such a mapping from H to K, show that it's a mapping, and then second, we're going to show that it's operation preserving. If it is, then it's a group homomorphism, just as before. Alright, part one. So we know that because alpha and beta are both group homomorphisms, they're both mappings. So for all elements G in the group G, we know that there exists H in the set H, group H if you like, and there exists elements in the set K such that alpha of G is equal to H and beta of G is going to be equal to K. So the first thing we do is define the function gamma of input corresponding to this G. So input is going to be H, right? In the domain H is equal to K. We trace it back essentially to the group G and then see which two elements does this map to, and then we associate those two elements via the map gamma. Before we get any further, I'd like to point out that there is not a unique way to do this, that we're not showing the existence of a unique homomorphism. And the reason for that is that the alpha map would have to be one-to-one, because there could be more than one G element which maps to this element H. We just know there exists at least one, and so long as we decide on our mapping gamma always taking a certain element to a certain output, it doesn't matter which one we actually choose. That is, it doesn't matter which pre-image of the element H we choose. And this definition is going to be valid, of course, for all elements H in the image of G under alpha. Alright, now we need to show that it's operation preserving. So for all elements, we'll call them H1 and H2, in the image of G under alpha, which we also know as H, it's going to be true that the product h1 times h2 is also going to be in the image of alpha. You can think of this in two different ways. This is always true because the image is a group, or because in this case the group H is the group image, so it's still going to be true. Now, since alpha is a mapping, there must exist elements G1 and G2 in the group G such that alpha of G1 is equal to H1 and alpha of G2 is equal to H2. It does not mean necessarily that these G values are unique, but there exists at least one. Now, since alpha is a group homomorphism, it is operation preserving, so that alpha of G1 times G2 must be equal to alpha of G1 times alpha of G2. But we just said that this is just H1 and H2, right? So we have that alpha of G1, G2 is equal to H1, H2. Now for whichever G1 and G2 we picked in G, it's going to be true that gamma of H1 is defined to be beta of G1, right? And gamma of H2 is defined to be beta of G2, for whichever G1 and G2 we pick, because they're not necessarily unique. And also by the definition of gamma, we would have that gamma of H1 times H2 has to be equal to beta of G1, G2, since we saw that alpha maps G1 times G2 to H1 times H2. But because beta was assumed to be a group homomorphism, we have that it is operation preserving, right? But then each of these, we said, coincide with the value of gamma of H1 and H2 respectively, so that this is equal to gamma of H1 times gamma of H2. Now look what we have by transitivity of the equal sign here, that gamma of H1 times H2 is equal to gamma of H1 times gamma of H2. In other words, the mapping gamma is operation preserving, so that it is indeed a group homomorphism from H to K. All right, let's first consider a mapping from the non-zero complex numbers under multiplication to the positive real numbers. I'll just say x and r such that x is greater than 0, and this is going to be x and r times. I'm using this to mean that we're talking about the real numbers under multiplication here. And then consider this mapping given by f of z, complex number z, is equal to the modulus of z. And if you don't recall what the modulus is, we have z equals x plus iy, right, where x and y are real numbers. This is our generic complex number with I as the square root of -1. And then the modulus of z is going to be equal to the square root of x squared plus y squared. And when I say the square root, I mean the positive real square root. All right, so obviously every non-zero complex number, actually even with 0, has a modulus, so we don't have to worry about this failing to be a mapping. Suppose we have two non-zero complex numbers. We'll call them z and w. And we want to consider f of the product z times w. Well, this is going to be equal to the modulus of z times w, which, in case you're not familiar with the rules of the modulus and more generally norms, I will just write this out in terms of components. So let's call z equals x plus iy, and w is equal to u plus iv. Real numbers x, y, u, v is going to be equal to x plus iy times u plus iv modulus is going to be equal to, we're going to have x times u minus, this is going to square to -1, minus yv plus I times yu plus vx, right? Yu plus vx norm. And then the modulus of this is just going to be equal to the square root of xu minus yv squared plus, we'll write it this way, xv plus yu squared. Now if you square those two terms, we're going to get this is equal to square root of x squared u squared plus y squared v squared minus 2xu yv, and I'll just write this on the next line, plus dot dot dot, plus x squared v squared plus y squared u squared, and we're going to have plus 2xv yu, if you will. So the square root continues and then ends. Alright, now what we'll notice is that this is the same as this, so those cancel each other out, and then we're left with is equal to square root of, and let's combine some terms. Namely, let's factor out x squared and y squared. So we'll have x squared times u squared plus v squared, and then plus y squared times u squared plus v squared. And then this is just equal to the square root of x squared plus y squared times u squared plus v squared. But we can split up the roots so that this is equal to root x squared plus y squared times the square root of u squared plus v squared. But notice that this is equal to the modulus of z, and this is equal to the modulus of w. But our function, of course, is to take the modulus, so that this is equal to f of z times f of w. And thus we have shown that our function, the modulus, is indeed an operation-preserving function from the complex numbers under multiplication without zero to the positive real numbers under multiplication. Thus, it is a group homomorphism. Alright, so for all x in the real numbers such that x is greater than, just greater than 0, we want to show that there exists a complex number, at least one anyway, that maps under this modulus operation to that real number. So that if we have modulus of w is equal to, say, square root of u squared plus v squared, right, where w is equal to u plus iv again, we want to show that there exist u and v such that this is equal to x, right? Now if we square both sides, we see very quickly that this is just u squared plus v squared equals x squared, which is to say that in the complex plane we have our real part of w squared plus our imaginary part of w squared is equal to the number x squared. This is just a circle in the complex plane centered at the origin with radius x, right? So we have an entire circle, and this is distance x from the origin, so that any point on this circle, which can be parameterized in polar form as x e to the I theta, is going to satisfy this for any real number theta. Thus there exists at least one, in fact there exist infinitely many complex numbers w, namely x e to the I theta, such that the modulus of w is equal to x. Thus the modulus operation is an onto mapping from the complex numbers without zero to the positive real numbers. Alright, last time I defined the automorphism group for you just a little bit more rigorously by showing that the composition of two automorphisms is yet another automorphism. And thus, under the operation of function composition, the automorphisms of a group form a group in their own right. So let's exercise this by finding the automorphism group of the group Z4. So Z4, if you'll recall, is the set 0, 1, 2, 3, right? So addition modulo 4 over the integers. All right, let's just start with bijections and then build up automorphisms from there. So how many bijections are there going to be from a set with 4 elements to itself? Well, it has to be onto and 1-to-1, so essentially it's just a permutation of 4 symbols, right? In which case there are 4 options for the first element for where this gets sent, right? It could get sent to 0, 1, 2, or 3. Then there are 3 options for the second, 2 for the third, and just 1 left over. Thus, what we're saying is that the order of S4, right, the symmetric group on 4 symbols, is going to be equal to 4 factorial, or 24 different bijections. However, not all of these bijections on the group Z4 are going to turn out to be automorphisms. So if we have a mapping from G to H, which is a group homomorphism, then phi of E sub G, the identity element in the group G, is going to be equal to the identity in the group H. So we only need to look for those ones which fix 0. Alright, well that's going to knock out a lot of possibilities. Namely, we're going to want to divide by 4, and now we only have 6 possible mappings. Alright, so we've shown that 0 must get mapped to 0. What else must be true? Well, I want to also make the case to you that the element 2 must get mapped to the element 2, otherwise it's not going to be an automorphism. Alright, so the full explanation of why 2 must map to 2 comes next time when we talk about cyclic groups. But for right now, just consider this. 2 plus 2 mod 4 has to be 0, of course. So that means that any automorphism, we'll call it phi, being operation preserving, this must be equal to phi of 2 plus mod 4 phi of 2. But we know that this is the identity, right? And we know that the identity is fixed, so that this must also be equal to 0. But this can only be true if the element it gets mapped to is also 2, because it is the only idempotent element, if you will. The only element other than the identity, which it plus itself is equal to the identity. Thus, any automorphism from the set to itself has to map 0 to 0 and 2 to 2. So now we are left with 2 options, mapping 1 to 1 and 3 to 3, or 1 to 3 and 3 to 1. And you can check both of these are indeed automorphisms, so that we get a set with 2 elements, and in fact, because of what we showed last time, the composition of automorphisms is an automorphism, it's going to form a group. And there is only one group up to isomorphism which has exactly 2 elements. That's going to be Z2. So that we can say confidently the automorphism group of Z4 is isomorphic, I'm using this symbol to mean isomorphic, that's common, to the group Z2. Of course, if this is still not clear, notice that the composition of automorphisms is an automorphism, so clearly it's going to form a group, right? And then if we take the mapping 1 to 3 and 3 to 1, and then we take it again, it's going to be idempotent, right? Which is the same as in the group Z2 when 1 plus 1 is equal to 0, right? And the identity, of course, is just 0, which would correspond to mapping 1 to 1 and 3 to 3. So it really is true that this is an isomorphic relationship, right? This element corresponds to a unique element in here, which is mapping 0 to 0, 1 to 1, 2 to 2, 3 to 3, and this element corresponds to a unique mapping in the automorphism group of Z4, which is 0 to 1, 1 to 3, 2 to 2, and 3 to 1. And so we get that these really are isomorphic groups. Alright, I'd now like to introduce a new variant on an old friend. So the general linear group, 2 by 2 matrices with now, instead of real or complex valued entries, let's take entries in Z2, right? So we're combining modular arithmetic with our matrix groups. This will be lots of fun, right? What does this consist of precisely? It consists of all 2 by 2 matrices A, B, C, D, such that A, B, C, and D are in the set 0 and 1 under the rules of modular arithmetic, so that 1 plus 1 is 0, 0 plus 0 is 0, 0 plus 1 and 1 plus 0 are both 1, right? It's Z2. All right, so I wrote all the binary valued 2 by 2 matrices right over here. And then of course we want to reduce this list by looking at the ones which aren't invertible. And this is actually pretty easy for 2 by 2 matrices if you know a little bit of linear algebra. So any matrix which has, for instance, a repeated row or a repeated column is not going to have a non-zero determinant, so that we have that one is not in there, this one's not in there, that one's not in there, that one's not in there, that one's not in there. And of course the 0 matrix is not going to be in there anyway, because the identity in this case is going to be the multiplicative identity, which is this 1, 0, 0, 1, right? The identity matrix as we usually normally call it. And then of course we also want to knock out the ones that have 3 zeros in them, because this is going to have determinant 0 as well. 0 times 0 minus 0 times 1, it's going to be 0. So we get rid of that, we get rid of that one, we get rid of that one, and we get rid of this one, and we are left with a measly 6 matrices. And I will write them out. Alright, so what we are left with is just these 6 matrices. We have the identity matrix, something which looks sort of like that, only on the other diagonal, and then we have the 4 matrices with 3 1s in them and 1 0. Now what I want to do is show that this group is isomorphic to S3, the symmetric group on 3 symbols. Alright, so I'm going to use the same notation that I introduced before for talking about S3, where we have our 3 sigma elements, which just switch 2 elements, right? And then we have pi r and pi l, which are going to be the ones which send 1 to 2, 2 to 3, and 3 to 1, right, cyclically in one direction and then cyclically in the other direction. Now the first thing we know about group homomorphisms, even apart from isomorphisms, is that the identity must be sent to the identity. So if we are to construct any homomorphism between these two, phi gl of 2z2 to the group S3, we are going to have that phi of the matrix 1, 0, 0, 1 is equal to the identity permutation in S3. Alright, so this is going to map to this, right? Identity to identity. Now, where do we possibly begin in mapping the other 5 elements? Right? We have 3 elements which are sort of the same thing going on here, and then 2 which are similar right there. But here we have 4 matrices which look essentially the same, and then 1 oddball. Are they possibly going to pair up well? Well, watch this. So the matrix 1, 1, 1, 0, if we square it, is going to give us 1 plus 1 is 0, 1 plus 0 is 1, 1 plus 0 is 1, and 1 plus 0 is 1. So we're going to get that this matrix squared is equal to that matrix. So then this matrix cubed is going to be equal to 0 plus 1 is going to be 1, 0 plus 0 is 0, 1 plus 1 is 0, and 1 plus 0 is 1. And this is none other than the identity matrix. So we have that this matrix cubed is equal to the identity matrix. Well, if you'll notice, this is exactly like the cyclic permutations, right? Pi r or pi l. So just by convention, I'm going to map this matrix to pi r. Now let's look at this matrix 0, 1, 1, 1, 1. Okay, if we square this, it's going to be sort of a similar story. We're going to get 0 plus 1 is 1. We're going to get another 1. We're going to get 0 plus 1 is 1, and 1 plus 1 is 0. And then we actually already took the product. If we 0, 1, 1, 1. We already took this product last time. It's the same product that showed up before, so that this is equal to the identity. So that this matrix cubed is also equal to the identity. So then it makes sense to map this last matrix to the other cyclic permutation pi L. Now what has left to be shown is that these three matrices square to the identity. If they do, then there's going to be a perfect correspondence and structure here, which is what we want. So if we take the product of this one with itself, we get 0 plus 1 is 1, 0 plus 0, 0 plus 0, and 1 plus 0. It is the identity matrix. So let's map that to this one, just by choice. Alright, now let's multiply this one by itself. This is going to give us 1 plus 0 is 1, 1 plus 1 is 0, 0 plus 0 is 0, 0 plus 1 is 1. This one squares to the identity as well, so let's map that one to sigma sub 2, 3. Alright, and for the last one, we want to show that this squares to the identity, so 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0, and 0 plus 1 is 1. And it works. So we're going to map this element to sigma sub 3, 1. Alright, well, in selecting this map, we've already shown that it's true that the preservation of each element squared or cubed is going to be right. Now the question is, did we get these sort of mixed products right? Alright, so if on the set of three symbols we switch the second and third and then follow that by switching the first and second, this is going to be the same as our left permutation. Likewise, if we were to do it in the other order, sigma sub 2, 3 times sigma sub 1, 2, this is going to be equal to the right permutation. Now if you multiply the matrices corresponding to sigma 1, 2 and corresponding to sigma 2, 3, we get this product, 0, 1, 1, 1, which, what does that get mapped to? That's going to get mapped to, where is it? Right here, pi L. Perfect correspondence. Similarly, you will see that if you flip these two, you're going to get the opposite thing, which has got to be pi R. Alright, so once we've gone through and verified that every product is preserved, then it is true that this mapping is going to be an isomorphism. And even if I fudged the details, which I don't think I did, but just saying, GL of 2 we're going to find, GL of 2 Z2 is isomorphic to the symmetric group on three symbols. Now in most homomorphisms and isomorphisms, you don't actually have to look through at every two elements individually, right? There's usually some rules that you can prove it all at once. In this case, there's not, so we mapped element-wise, and it can get a bit tedious. But the point is, they are isomorphic. And you wouldn't expect that a group of matrices under matrix multiplication with values which are determined by modular arithmetic is structurally, it's no different than permuting three symbols. Isn't that interesting?